giving this choice for presenting my result. For a century, the summer insolation in the North Hemisphere has proposed as a key pacemaker of astronomical climate change. And this kind of climate change features temperature and ice volume dramatic change in higher latitude, but for the lower latitude, the temperature change is relatively minor. And also, they have a cycle of obliquity and eccentricities. But for lower latitude, climate change features very different than high latitude. The primary period of this change are precession, and also the characteristic is wet and drying over time. So you can find still awesome from both Brazil and China showing a similar period of this change. Classical theory suggests that the summer insolation increase in the North Hemisphere corresponds to decreased summer insolation in the Southern Hemispheres. So the IPCZ will shift it towards the warmer hemispheres. So we expect that the North Hemisphere and South Hemisphere will have an anti-relationship between for the wet and dry conditions. And also, we expect that the North Hemisphere reached the wettest period around 10,000 years ago, when the North Hemisphere summer insolation was peaks. But with absolutely dated record, like in China, we find that many of the wet period is not really 11,000 years ago. Some of them are in 8,000 years, and some of them are in the late Holocene. And this phenomena does not only exist in China, but also in North Africa. As you can see, the peak insolation is around 11,000 years ago, but the wettest period of Africa is around 8,000 years. There's an age difference of 3,000 years. In the past 2 decades, there's many hypotheses proposed to explain this age difference between the maximum insolation and the wettest period in the north or southern hemispheres. And this suggests that climate change is very complex, especially in the past 20 years. There's variation in CO2, and there's internal climate feedback, and also AMOC and ice sheet, but not really linear response to the peak insolations. And also there's sea level fluctuation, which impact the moisture source region. But actually, the last 20,000 years is not the ideal time interval to examine this problem, because the eccentricity is relatively small, and the perihelion and aphelion have not much difference. And if we take a look at the record covering many precession cycles, you will find that the age difference or the phase difference exists not only in the recent 10,000 years, but also in many precessional cycles, like this one, the Brazil wet period in the north part of Brazil. Following the insolation in March or April. Taking a look at the record from Malaysia, they have age difference, phase difference of 5,000 years to the north hemisphere, and another 5,000 years difference to the southern hemispheres. So why is that? To understand this problem, we need to first to understand what is precession. This seems very simple, but not that simple. In Chinese, precession is also called a difference in a year. Currently, we all use tropical year, which measures the year by the changing position of overhead sun. But this is not really the circle of Earth's revolution around the sun. There's another year called anomalous year. And this year measures the timing of perihelion. Each time when it passes perihelion, then it's finished cycle. So if we take a look at this problem from a tropical year perspective, you will see that the closest point when the Earth and Sun takes place from spring to the summer, and then autumn, and then to winter. This is traditional view. But if you take a look at this problem from the perspective of a normalized year, it's very simple. Every year when the Earth passing through the closest point between Earth and Sun, the perihelion, the overhead sun position changes from the southern hemisphere to the equator and then to the north hemisphere and back to the equator. So precession is a function of latitude, the latitude where the strongest solar radiation is concentrated. With this idea, we developed one dimension series. We propose the strongest solar radiation corresponds to the strongest ITCZ and strongly lengthy temperature contrast. And this will increase the precipitation in the corresponding latitudes. To test our hypothesis, we run a climate model simulation to reconstruct four precession cycle, and we evaluate the precipitation in 24 degrees, 10 degrees, equator, 10 south, 24 south, and this is dashed line showing the latitude migration of this perihelion latitude. As you can see, wherever this latitude migrates, the local precipitation will be peaks in their precession cycles. And to demonstrate further, we also selected Steve Olsen from China, Malaysia representing equator, and then Brazil representing the southernmost latitude. And as you can see, when it moved to China, and then China precipitation is relatively strong, and then Malaysia, Brazil, equator, and then north, equator, south, equator, like that. To give a summary, so for a century, the summer insolation are proposed as a key pacemaker of climate change. I believe this is true for the high latitude, because high latitude ice melt and accumulate depend on the summer insolation. But for lower latitude, ITCZ is the major characteristic of climate. ITCZ follows the strongest sun on annual cycle, but also on orbital cycle, we propose that low latitude precipitation, strongest precipitation, also follow the strongest sun. The strongest sun is the time of perihelion. That's all for my talk. Thank you.
Thank you for staying in time.